numbers alpha written in lowest terms with height not exceeding t. So I can just offer you some examples. B of 1 is 1. B of 2 is 3. And in red, you see the number 19, which is related to, illustrated by the example on the previous slide. There are 19 positive rational numbers with height not exceeding 5. And in this way, if you let t walk through the positive integers, you get an interesting sequence of positive integers. Is there a formula for this sequence? And as t goes to infinity, what are the asymptotics of this sequence? These are natural questions, as I said, you would ask in a course. As an exercise in this course, you can assemble the following formula. If n is a positive integer, then b of n is negative 1 plus 2 times the summatory function up to n of Euler's phi function. The reason for that is you have x over y as well as y over x. So every pair x over y positive integers that are co-prime give the same height but twice. And you overcount exactly once, which is the point for the negative 1. 1 over 1 and 1 over 1 are still the same values. What's much more interesting, however, is that you can use properties of the zeta function to show that as n goes to infinity, b of n is asymptotic rather tightly to 6n squared over pi squared. So counting the number of rational numbers with bounded height is a simple exercise in your first course in number theory. And just to illustrate how rapid the convergence is, if n is 100, it turns out that b of 100 is 6,087, and the asymptotic on the right gives you something very close, 6,079.271. Now, when you teach this course, you probably want to emphasize that there's a lot more going on in this example than, say, meets the eye. Because you can view the field of rational numbers as an additive group. And so when you take into account signs, what you're really doing is you're counting the number of elements in this group bounded by height. And so by taking into account signs, b of t without the plus under q is 12t squared over pi squared, and that gives us a lot of information about this group. Of course, the height of 0 is 0, and the point I want to make is that q is just an example of a group for which counting points by height is reasonable and important. These kinds of ideas are pervasive. So this talk is about counting points on elliptic curves bounded by height, which is a very old problem. In fact, it's perhaps the oldest problem in the theory of elliptic curves in the wake of the proof of the finite generation of rational points. The theorem, of course, I'm alluding to is Mordell's theorem, that if you have an elliptic curve E over Q, then the group of rational points over Q, in this case, is a finitely generated abelian group. I think you all know the group law, so let me just say the picture explains it all. And of course, what that means when we say that the group of rational points forms a finitely generated abelian groups is indicated here in the box at the bottom. It says that as a group, the Q rational points of E are isomorphic as a group to some torsion subgroup in direct product with a number of copies of Z. What is R of E? E is a number of copies, it's the rank, and so that's some non-negative integer. If you've never done this before, let me just show you this picture that I took from the internet. Here's an example of some special instances of computing with the group law on the curve y squared equals x cubed minus 36x. And the only point I want to make about this picture is that, well, starting with the point -3,9, you get a bunch more points, and their heights, the complexity, the number of digits that are required to write down each of these rational numbers grows very quickly, much larger height. So you could ask, if we want to count the number of points of bounded height on an elliptic curve, or more generally any abelian variety, what do you expect to get? So naively speaking, the question I'm asking is there an elliptic curve point count analog of the formula 12t squared over pi squared that I started this lecture with? And of course, this question is trivial for rank 0 curves because the only asymptotic you want to write down for a rank 0 curve is the asymptotic which identically equals 0, or the order of the torsion points if you like. And so the real question is, how does the rank actually impact these counts? The larger the rank, you expect to have more points on these curves. How does the growth of the rank or the variation in rank impact these counts? Well, a lot is known about that. So, but before I get there, let me fix some notation. I have to explain what we mean by computing the height of a point. So throughout this lecture, I'm going to let P be an arbitrary point on an elliptic curve in short Weierstrass form. So that's a curve of the form y squared equals x cubed plus a4x plus a6. Throughout, I will assume a4 and a6 are integers. And for curves in this form, every generic point has the indicated shape, a over c squared, comma, b over c cubed. The naive height of a point, h of p, is just the height of the x-coordinate. And so it's the maximum of the absolute value of a and c squared. And as much as we'd like to work with naive quantities, for the purposes that I'm about to explain, the naive height is not quite good enough. The logarithmic height is a little bit better, and it's just h sub w of p, w for v. That's the logarithm of the naive height of the point p. But even the logarithmic heights are not quite perfect for what we want to study. The perfect height is the canonical height discovered by Néron. Néron recognized that if you start with a point P and you consider the infinite sequence of the heights of np over n squared, as n goes to infinity, that the sequence is a Cauchy sequence. And so as n goes to infinity, you can define a canonical height to be the limit of these numbers. And for many reasons, this is the perfect height, as I shall now explain. In terms of a numerical example, if you consider the curve as shown here, y squared equals x cubed minus 3x minus 4, your computer will tell you that the rank of this curve is 1. A canonical generator could be chosen to be this point P, 8, 22. And if you have Sage Math that has implemented Néron's formulas, you'll find that height of P1 is around 1.107. So one of the nice properties of canonical heights, mirroring the statement that the height of the rational number 0 is 0 and is the only one with that property, the nice thing about the canonical heights is that a point is torsion if and only if its canonical height is 0. And for those of you who want to do some computational number theory and might be stymied by the requirement for computing Cauchy sequences, limits of sequences, there's a well-known lemma, theorem of Silverman, that says that the difference between the canonical height and the logarithmic height is bounded by a constant depending on your curve. So loosely speaking, canonical heights and logarithmic heights are essentially the same for the purposes of doing analytic number theory. So the natural questions, I think, that stand out, and these go back 100 years, are as follows. Can someone prove upper bounds for heights of generators, thereby giving a finite algorithm for computing the rational points, right? The number of rational numbers with bounded height is finite. And so if you could prove upper bounds for the heights of generators of curves, that would be extremely useful for the computational question of computing explicitly Mordell groups. And in particular, along the way, it would be nice to prove a formula for the rank that would therefore simplify such an algorithm. So of course, what I'm describing here is not just the stuff of computational number theory. I'm really just trying to rephrase the first problem that exists with regard to computing elliptic curves. And just to emphasize what these two open questions are, the proposed solution to these two open questions is the famous Birch-Swinnerton-Dyer conjecture. So I just wanted to illustrate that back in the day when Birch and Swinnerton-Dyer were formulating the conjecture, really what they had in mind is, are there methods and tools? Is there a theory that would allow us to answer the two open questions above? Because if so, then that would give rise to this algorithm. So that's the stuff about upper bounds. But the point of today's lecture is about lower bounds for rational points, which are also important. And this is the topic of a general conjecture due to Serge Lang. And let me state this conjecture in the case of the setting of today's talk, elliptic curves over the rational numbers. Lang conjectured that for every non-torsion point P, the following are true. So for the rest of this talk, P, a point P will not be torsion, but we just declare that 0 isn't interesting. I want to study the points of infinite order on elliptic curves. So for the rest of this talk, P will be a non-torsion point. Lang conjectured that there should be a universal formula depending only on the model of E, right? That offers a lower bound for the canonical height of P. Independent of what P is, just as a function of E, there should be a lower bound for these heights. And he proposed a shape, a type of formula for this lower bound, and that's the second part. The part 1 is the weak Lang conjecture. Part 2 is more precise Lang conjecture. And what he conjectured is that the canonical height should grow at least linearly, or should be at least a linear function in the logarithm of the absolute discriminant of your curve. They're constant C1 and C2 that would be universal, absolute, but roughly speaking, the naive height of a non-torsion point should grow be at least as large as some linear function in the logarithm of the absolute discriminant, which is his precise recipe for universal formula depending on the model of E. So what do we know about Lang's conjecture? Okay, and as I mentioned, Lang has a more general family of conjectures for abelian varieties over number fields where part 1 is still true, except you replace E by the generic variety and constant and some dependence on the number field. And part 2 is slightly more complicated similarly, but where you place the discriminant of an elliptic curve suitably for abelian varieties, and there's some input coming from the complexity of the number field. So what was known about this theorem? Well, if you were like me and you were a student in the 80s, you would certainly be aware of these very famous works of Hindry and Silverman from the 80s. And it says the following. In a beautiful paper, series of papers actually, they prove that Lang conjecture is true for elliptic curves with algebraic integer J invariance. That's rather sparse, okay, but this is a theorem for elliptic curves with integer J invariance. They have a theorem also for all elliptic curves, but it's somewhat unsatisfying. Their theorem says that Lang's conjecture is true, assuming the ABC conjecture. More explicitly, in much more recent work, Botissier, Hindry, and Pizzucchi proved that there exists an effectively computable constant C, for which the canonical height is bounded below by this constant times this expression. This expression is the square of the order of the torsion group over h log 3 squared times log 3h to the 4/3, where what is h? H is the maximum. It's essentially you should think of it as being the logarithmic height of the J invariant. Okay. All right. So the second theorem definitely offers a solution to Lang's weak conjecture. And but more generally, as you can see in the theorem above, that the truth of Lang conjecture seems to rely on the ABC conjecture. So some comments on that. We don't have a recipe for computing C1 and C2 in Lang's conjecture, and that's a bit of a mystery. So with regard to the work of Hindry and Silverman, this is a natural question. Can we make any sense out of C1 and C2? But perhaps the most significant part in terms of reflection for the state of art is the following. Outside of Japan, the ABC conjecture still seems to be a conjecture. And so this theorem is conditional. So the Hindry theorem, Silverman theorem, as deep as it is, no matter what, is still far from the end of the story. And the Botissier-Hindry-Pizzucchi theorem is not explicit. This is one of those things in analytic number theory where you talk about the difference between effectively computable and explicit. Things that tend to be effectively computable but are not done so are often targets of opportunity. They're not explicit. So what I want to do in this talk is take a completely different direction and tell you what we can prove unconditionally about Lang's conjecture using class groups, which is the topic of this conference. So our approach is completely different, but I don't want to I don't want that to sound like that's boasting. No, it isn't boasting. The approach that we want to take goes back to the original ideals of Mordell, when people were first proving that these groups of rational points are finitely generated. Sometimes it makes sense to go back to the very beginning, which is what we do. I will offer you the first unconditional explicit lower bound for canonical heights. And for many curves, this is an improvement of Tussier, Hindry, and Pizzucchi. So what does our theorem say? Our theorem says that if you take any non-torsion point in an elliptic curve, you can bound this height from below in terms of explicit constants that are not new to us, constants that already come naturally because they arise from the interplay between the linear algebra explaining calculations of heights, height pairings, regulators, and the arithmetic of the group law. So throughout this talk, and it'll come up a few times, I want you to remember this constant called C of E. If you are handed an elliptic curve with positive rank, R of E, we for free can calculate this constant C of E in terms of quantities that we expect. So C of E will be defined to be the order of the torsion subgroup over Q, divided by the square root of the regulator, times the volume of the unit R sphere. Okay. Remember, if under height pairings, you were able to map the generators just to the ordinary R lattice, ZR, right? Counting the number of points would be more or less equivalent to computing the volume of omega R when scaled with respect to the group law. And what I've just described isn't actually far from what our idea is. So although it is rarely written this way, I'd like to emphasize that what the Mordell-Weil theorem really says, remember the proof of the Mordell-Weil theorem is an exercise in heights, right? But if you use that exercise in heights and descent and just write down just a little bit more, what the proof of the Mordell-Weil theorem says is much more than that the order of that the group is finitely generated as an abelian group. In terms of the height counting problem, it says this: if E is an elliptic curve with rank R positive, the number of points in E with canonical height bounded by T is given by an asymptotic formula. It's this constant above times T to the R over 2. This is more or less what Birch and Swinnerton-Dyer had in mind as a starting point when they formulated the Birch and Swinnerton-Dyer conjecture. What would be a beautiful model for computing these point counts? How would you access the rank if you had the ability to compute these? And that's where they recognize the connection between the power of R with here with zeros of L functions, and now you know the rest of the story in terms of the formulation of PSD. So to get to our results, let me again fix notation. E again throughout is an elliptic curve with short form. And the most important thing I want you to remember is this polynomial. For every elliptic curve in short Weierstrass form, write down this polynomial in T, which is dE of T, which is 4 times T cubed plus A4T minus A6. The A4 and A6 are the short Weierstrass coefficients above, and that minus in front of A6 is not a typographical error. Plus A6 turns into minus A6 in this polynomial, and that's already a strong hint. We're already trained in the theory of elliptic curves to understand that we can learn a lot from elliptic curves by studying their quadratic twists. And in many instances, taking an imaginary quadratic twist is the one that gives you more information. And so what I want to emphasize here is that the A6 term in this normal form is the only power of X, the only term whose degree in X is negative. Odd is odd. I'm sorry, it's even, is even, right? X cubed and X to the 1, they are both odd. This A6 is the only one with even degree. So the theorem I'm about to state is not quite right. but for the purposes of the talk, I state the moral equivalent of the theorem. If you want to find the exact statement, you can read about it, that our paper is published, and you'll see a quantity called delta of E, which is the difference, an upper bound for the difference between the canonical height of all points on curves and the logarithmic heights. These are numbers that Joe Silverman in the 80s proved can be explicitly bounded as a function of E. And I want to say, in many cases, for a large proportion of E, and in fact, over 50% of the elliptic curves, this delta E can actually be taken to be 0. So that does not mean that the maximum of these differences is 0. It means that if you argue slightly for over half of the curves, the manner in which delta E arises doesn't even arise. Okay. By the way, this is related to the statement that over half of the elliptic curves ordered by height have trivial Tamagawa product, which I don't think was very well known or even expected to be true, but this is something I proved about a year or two ago. The probability is greater than 1/2 that if you pick an elliptic curve at random, the Tamagawa product will be exactly 1, despite the fact that we know that there is no such thing as an elliptic curve over Q with good reduction everywhere. From the perspective of the Burton-Swinnerton-Dyer conjecture, that obstruction over half of the time does not really appear in point counts. So our main theorem is this. So let me remind you, and I want to emphasize, dE of t is cubic. It's this cubic polynomial in t derived from the coefficients A4 and A6 in this way. And our theorem says the following. Suppose that t is a positive integer for which this double inequality is true. So let's just emphasize. dE of t is a cubic polynomial. The denominator here is quadratic. So asymptotically, the expression in the middle is linear in t, right? dE of t is cubic. The denominator is quadratic. So this middle expression is linear in t. So choose any positive integer t that satisfies this double inequality. And of course, because the t squared over 4 is quadratic, it says if there are any t that fail this, there are most finitely many that fail. So this inequality, double inequality, holds for all but finitely many t. So you pick one. Then, if p is any non-torsion point, we have that the canonical height of p is greater than or equal to the expression on the right that only depends on E and the value of this polynomial at t and the class group of discriminant minus dE of t. So this conference is about class groups. And I wanted to, when I saw that that's the topic, I wanted to talk to experts who study class groups and show how understanding class groups pertains and has implications for finding points bounding from below heights of points on elliptic curves. So again, this double inequality holds for all but finitely many t. I'm taking the log of this rational function in t. So this grows linearly in t. Okay, and the class number, as you know, grows something like the square root of the discriminant. And so this offers infinitely many lower bounds, explicit, completely explicit for these canonical heights. And as I said, what is capital H? It's the Kronecker-Hurwitz class number for discriminant minus dE of t. I forgot the minus sign. So of course, this doesn't require that minus dE of t be a fundamental discriminant. It can be whatever discriminant which you'd like, which is guaranteed for free by the divisibility by 4 that appears in the definition of D. So as I said before, but I have to read it because it's on the slide here. For every elliptic curve, this theorem applies for all but finitely many choices of t. What choice of t is best? Almost always it's the smallest choice of t that satisfies this double inequality. Will this be the largest? Why is, okay, so anyway, yeah. So here's an explicit lower bound. So this is an explicit lower bound, but it's subject to computing class numbers. So if you want to be completely explicit, we get this. So for every one of these positive integers t satisfying this double inequality, for every non-torsion point, here is just an analytic formula a lower bound for the canonical height of P. The only thing that is done here is that the Kronecker-Hurwitz class number has vanished and has now been replaced by this analytic expression in the square root of absolute discriminant times this logarithmic factor, which is a standard upper bound for class numbers that you can obtain by Abel or partial summation. So what do I like about this? The quality of this theorem in many cases already improves on the works that I mentioned above. It certainly doesn't depend on any conjectures, and it is unconditional. So how does this work? So as I said, okay, so how does this work? The idea is actually quite simple. The idea is that what I want to do is that I want to map points of infinite order on the elliptic curve to quadratic forms and then use fact about class groups. At first glance, this looks impossible because the elliptic curve, they're infinite groups and the class groups are finite groups. How can it be that some small finite group can tell us information about these infinite groups of rational points? It turns out it's quite easy to do. So let me explain, and I'm going to do it in completely explicit terms. Consider, for the purposes of a notation, binary quadratic forms capital F, whose coefficients are integers a, b, and c. And just to recall, that the discriminants are what you expect, b squared minus 4ac, and these binary quadratic forms are positive definite when they have negative discriminant with leading positive coefficient a. As everyone here, I think, knows, because this is where the modular forms generally come into the theory, but I don't need any modular forms for this talk. Let me just remind you that SL2Z acts on binary quadratic forms of fixed discriminant by this factor of automorphy. These changes are variable. And of course, the point is that the discriminants are fixed under these SL2Z actions. And one of the reasons we like this is that you have some infinite set that can be studied by, that can be reduced to a finite set of representatives, the class group, which is the content of this famous theorem of Gauss, that the discriminant minus d quadratic forms form groups, and this is under the equivalence of SL2Z action, and these groups are all finite. And moreover, as we know, these class groups are the first examples of class groups in class field theory in connection with the Galois theory of various types of unramified abelian extensions of imaginary quadratic fields. So this little theorem is the beginning of a very big story. So here is just some notation to in case I need it later. So if I drop x and y and use these triples, for example, in the second example, 1, 0, 21, you know what I'm talking about. I'm talking about the quadratic form x squared plus 21y squared. So again, the idea is if we want to get lower bounds for heights of rational points on elliptic curves, I want to use the arithmetic of these most classical of groups. So the ideal class group, you know, is related to these class groups. They are related by means of this mapping, where a quadratic form with coefficients a, b, and c maps to these ideals. And of course, we know and are unfortunately trained to think that class groups are important only because of their measurement for failure to unique factorization. So one of the points I'd want to make is that actually, on the contrary, the size of the class group, as I will explain, has everything to do with the complexity of heights of points on elliptic curves. So if you've ever wondered what the role of the work of Goldfeld is in the famous Goldfeld-Gross-Zagier theorem giving lower bounds for class numbers, you've heard many times, if you could find an L function that had a higher order of vanishing, or equivalently, an elliptic curve with large analytic rank that is provable, then you can get a lower bound on class numbers. What I'm doing is I'm doing something a little bit related to that, where I'm showing how explicitly the arithmetic of the class number is related to the arithmetic of the curve, which is why I want to take the original approach of viewing the proof of Mordell's theorem as an asymptotic for counting heights. There's no mystery for why the higher order 0 implies higher order class numbers. I think I spoke about that last year in this conference. So let me remind you that the order of that's actually very important, right? You can get effective lower bounds for class numbers of the shape log to the 14th, not just log, if you use these connections. So the class numbers and L functions in the case that I need here are related just by the classical Dirichlet class number formula. So for fundamental discriminants, L minus D of 1 is 2 pi over root D times the class number. This is also easy to generalize. And in the spirit, I now realize here that I'm giving the lowbrow version of this talk. I apologize for this. I was a little bit sleepy. I have a more technical version, but let me say this anyway. So this theorem is a prototype for, of course, BSD and the Bloch-Kato conjectures. And the exercise for proving upper bounds for Kronecker-Hurwitz class numbers is to show that H of minus D is bounded from above by this expression, and it's a standard exercise involving partial summation. So the corollary I offered, which is the effective lower bound for rational points, depending only on the coefficients of E and this minimal T, makes use of this formula. So for the purposes of my talk, what I have to do is I have to give the first theorem, which is the theoretical lower bound involving these class numbers. So let me explain how that works. So our idea is simple. So given an elliptic curve E, again in short Weierstrass form, the minus D quadratic twist is given here. And one of the reasons that we care about these pairs of quadratic twists is that these curves are isomorphic over the imaginary quadratic field Q root minus D, but are generally non-isomorphic over Q. But you can use arguments coming from Galois cohomology to actually leverage the small difference that there is between imaginary quadratic fields and Q in families where the discriminant moves. So although I said this difference is quite small, the ramifications for these difference in families can be quite big, right? In a family of quadratic twists, you can have elliptic curves with rank 0, with rank 1. And I think in every family, we know that there will be elliptic curves with rank at least 4, right? There's a wide disparity, despite the fact that the variation of the class groups can be very minor. And the reason that that is allowed is that the role of the size of the class group appears in this logarithmic power on counting heights. And from the perspective of analytic number theory, you don't see that so easily, but the difference in the R and the point counting function by height is very significant in the group. The difference between rank 1 and rank 2 is significant for the group, but very minor with regard to the point counting function in terms of heights. So here's our simple idea, and then I'll make it explicit. How do we employ class groups to get lower bounds on heights of points of the untwisted curve, right? E is an elliptic curve, and I want to choose a suitable imaginary quadratic field whose properties make it possible for me to see information about the original E without worrying about the complexity of the quadratic field, or at least not worrying very much about it. So here's the idea. Suppose E is an elliptic curve with positive rank, at least 1. And now choose any quadratic twist that has a point called QD. This QD doesn't have to be a point of infinite order. It can be essentially any point where the X and Y coordinates are non-vanishing. So it could be a torsion point. So to choose any twist that has a point called QD, and my idea is to assemble a pairing on the rational points of E paired with the rational points in E minus D. E minus D could have rank 0. This could be a torsion group. But what is the point? I want to write down a rule. I want to write down a pairing that makes use of the coordinates, the model of E and the model of E minus D, such that the pairing takes a point, pairs of points P with this fixed point QD, and gives me a binary quadratic form of discriminant minus D. And what is my idea going to be? I'm going to vary the point P in this pairing so that I get a bunch of positive definite binary quadratic forms. And I claim that if we do this, and I say carefully here, but you'll see in a moment, it's actually not that carefully. If I do that, that automatically forces the canonical height of P, any P, to already be large. So there's a couple comments I have to make. If E has infinitely many points, and I'm studying the pairing of P with a fixed point QD, I'm getting infinitely many quadratic forms here. But in the class group, because the class group is finite, many of these will be equivalent. So you might ask, how in the world am I going to map an infinite set to a finite set and provably force that the canonical height of all the points I start with in E have to be large? So let me explain. All right. So here's the ideal class pairing first. So suppose E is given with a generic point P that is non-torsion, and let Q be in any point on the quadratic twist. Define alpha and G to be these quantities involving the coefficients of P and Q. Then I claim this following formula. As a function of alpha, G, and the points P and Q, I can define a positive definite binary quadratic form in the variables X and Y by this formula. In blue, you find an integer called L. L is just chosen to kill any denominators if there are any denominators left. All right, so this, you might wonder, is this definition well defined? Yes, there are always integers L for which this binary quadratic form is genuinely an integral binary quadratic form. All right, so and as you vary L, well, so let me just leave it at that. So if I give you so maybe you want to take a look at that. Are there any questions on this formula? So given a point P and a point Q on the quadratic twist, I'm giving you an explicit binary quadratic form that is integral, where L is chosen minimally to kill these denominators. All right, this is being recorded, so you can always save this later, but it's an explicit thing. So for an example, if E is this curve, it has rank 2, I believe. Choose these 2 points, P1 and P2. And on the minus 24 quadratic twist, there's a point called -3, 1. You can just check that. And if you let L equals 2 in that previous definition, you can work out these 2 quadratic forms. So this formula for this curve is very easy to work out. It's always easy to work out. It's actually harder to look at than actually work with. Gives these 2 quadratic forms with discriminant -24. They are inequivalent, and the class number is 2. So my first claim, but I haven't proven it, is that under very general circumstances, this pairing I've written down will allow you to compute these class groups, right? An elliptic curve, E, has infinitely many points. How hard is it for the infinitely many points on E to generate the class group? It's actually not hard at all, which is why this is, I think, a good idea for trying to use the class group to understand all these points. So what did we prove? So Michael and I proved the following theorem about this pairing. The following are true. First of all, this pairing is well defined, and it always gives you a positive definite discriminant -d quadratic form. Always gives you one. The question, though, is under what circumstances do distinct pairs of points give rise to distinct quadratic forms? I need to separate them. And we worked that out too. If you took pairs of points P1, Q1 and P2, Q2 in these direct products, then the resulting binary quadratic forms are equivalent in the class group if and only if one of these 2 conditions holds. The first condition is very easy to avoid, as I'll show in a moment. The second condition might look less easy to avoid, and that is actually the source of why it is possible for these infinitely many points to collapse into something called the class group, which is finite. But what you can show, and I'll show that in a moment, is that this condition in red, which forces the dramatic collapsing of an infinite group into a finite group, gives rise to something quite easy. You could ask, are there intervals of points in the Mordell-Weil group? And I'll explain that in a moment. Can you actually find intervals, which I'll define on the curve, for which this pairing injects into the class group? Because if you can do that, then you can carry out my simple idea. So the pairing that Michael and I write down is related and was inspired by earlier pairings discovered by Duncan Buell, Greg Call, and Soleng. I don't remember Soleng's first name. So here's a sketch of the proof of our main theorem. So as I mentioned before, and I made it a point, that what the proof of the Mordell-Weil theorem really is an asymptotic formula like this. The number of points of bounded height t as t goes to infinity is asymptotic to this very nice constant I know, coming from linear algebra, times t to the r over 2. But you know what? I don't care about the full Mordell-Weil theorem. I just want to find lower bounds for the canonical height of a fixed point. So instead of working through the whole proof of the Mordell-Weil theorem, let's go through the proof of the Mordell-Weil theorem to the rank 1 subgroup generated by P. The proof goes through rather easily. So I adapt that proof just to the rank 1 lattice generated by P. So it's well known, of course, and I made this a point earlier, that the canonical height of NP is the canonical height of n squared times the canonical height of P. This is what I said earlier when I said that Cauchy sequences are formed. That relies on this kind of formula. Therefore, if you're given a non-torsion point P, you can consider the rank 1 subgroup generated by P. And by this formula, it follows that the number of points in this rank 1 subgroup with height bounded by T is equal to this expression. Just equal to this expression, because this is an equality. It's equal. We have a formula for it. No asymptotics. I have a formula for it. And then when I take into account the torsion, so notice on the right-hand side, I haven't done anything. This is just using this formula. Somehow the arithmetic of E has to be inserted here. So if I just decorate this by recognizing that there could be a non-trivial torsion subgroup, I can now count the number of points in the rank 1 subgroup crossed with the torsion subgroup with height bounded by T, and that's at least this. Remember that heights of torsion points is 0. So when I work with canonical heights, these are explicit inequalities. So the idea is, how do I use this formula and get a lower bound for the canonical height, right? This is what I'm trying to get a lower bound for, the canonical height. Trying to get a lower bound for this canonical height in this denominator inside this square root. But this is really good, because if I want to get a lower bound for this, what I'm really just trying to do is excise this out from this formula and essentially want to put this on the left. So the idea is that I want to choose T carefully so that for the points in this expression above, the canonical height of every P is greater than some lower bound, but that happens to be chosen to be less than or equal to T, right? If I want to get a lower bound for canonical heights, I want to choose T sufficiently large so that this formula is already enough, because I'm only counting those points that might be an obstruction to this lower bound, right? If I count the number of points up to T, I could care less about the points with height higher than T, because the goal is to find a lower bound, right? Does that make sense? The goal is to find a lower bound. So if I choose T appropriately, the points not counted by this don't matter to my problem. All right. So what I want to notice is the following. If I choose the polynomial point, negative T1, this is generically a point on the quadratic twist of the function field over Q of T of E minus D of T. Indeed, if I take the quadratic twist by minus D E of T, so this is a slight normalization that I'm using in the proof. The quadratic twist there clearly has a point negative T1, because dE of T was defined to be up to sine this cubic polynomial. So I, for free, have a point. And for my pairing, I said, if I can take a pairing of a point with a quadratic twist that a priori has a point, then I have information. So for the purposes of this talk, although for the purposes of computation, this is far from optimal, for experts, you'll know that there'll be many elliptic curves with much lower height that have points. This is just a device for guaranteeing one. I'm going to restrict my pairing to the pairing of the elliptic curve I want to study, paired with E minus dE of t, and I'm mapping into this infinite family of class groups. And what is the point? Every time I choose a t, I want you to think I'm choosing this point Q, and I'm going to be varying the point P. So this is the magical step.
Yeah, Ken, sorry to interrupt. You have 1 minute, so maybe you can try.
Oh, 1 minute. Oh my God. So the magic is here. The magic is that if I choose T, what?
That's fine. Please continue.
Yeah, so this is the most important step. If you choose TE to be this function, we prove that this set of rational points in the curve injects into the class group. If you choose TE, this is the interval. If you choose TE for T, we prove that the points of infinite order with height bounded by that TE inject into the class group. By the way, you can make the class group large this way, but what I'm trying to do is I'm trying to make the lower bounds for the heights. And if you just work that all out, this then says that the number of points with bounded height, which is bounded at least by this, have the property then that the class number is at least this, right? When these points inject into the class group, it means that I can replace this left-hand side by a class number. Because of this injection, I can replace this left-hand side by the class number. So I know the class number is at least as large as this. But I want a lower bound for the canonical height. And of course, that just gives this literally just by rewriting this formula. And so we now note that the right-hand side is less than t whenever I choose TE to be this. So this is how I get that lower bound. It's very simple-minded. Very simple-minded, just thinking carefully about what the theory of heights, together with the theory of canonical heights, together with a little bit of linear algebra, and this new class pairing gives you this solution to Lang's conjecture. Great. So I guess I'm finishing up anyway. This theorem is the first unconditional and explicit solution to the weak Lang conjecture. And it's an improvement on things that have been published previously, and certainly by no means relies on anything like the ABC conjecture. It's simple-minded. Proving the weak Lang conjecture is straightforward. And in terms of an analytic formula for T, you get this. So I apologize if the right-hand side doesn't look very pretty, but the reason it might not look pretty to you is that in analytic number theory, you hide a lot of the constants and try to emphasize the role and the size of the quantities on the right. That's not what I want to do here. I want to give you a canonical lower bound that holds for all elliptic curves. And you can now see where the dependence on the curve comes in. It comes here in the logarithm of the model, and it comes here in a class number of the corresponding twist of that model. And then with that, I will end. Thank you very much.
Thank you, Ken, for the interesting lecture. Any questions, comments? Yes, one. Okay.
Hello, I hope you can hear me.
I can hear you.
Yeah.
I hear you like 5 times. It's reverberating. So I do my best to listen.
Do we know an example where the inequality is tight?
Oh, no, definitely not tight. No, definitely not tight. Nobody's inequalities, apart from assuming ABC, are close to tight.
So do we expect a much shorter bound to hold?
Oh, yeah. Yeah. And I can tell you where you can start, by the way. Can you hear me?
Yeah, sure.
I can tell you how to start. So my formula, if I want to find a lower bound for the canonical height of a point on E, using my pairing, the formula relies on finding a quadratic twist with a point. And I just, for convenience, use this quadratic twist by this polynomial dE of t. But every expert will say, you don't have to wait that long in discriminants to find a point. So anyone who thinks a little bit more carefully about finding a lower conductor curve that has a point will immediately do better than what we did. Immediately. And by the way, if you assume GRH, I didn't write this down, but if you assume GRH, you can show that 50% of the quadratic twists have rank 1 and 50% have rank 0. And you can give an upper bound for the discriminant that has the first twist. Just plug in that and you'll get a better theorem, and you'll actually might be very close to the truth. So you might be able to get a theorem that says GRH, which, do you understand what I'm saying?
Yeah,
If you bound by discriminant the first twist with rank 1 and bound the height of the generator, that use that for the point Q, you might actually prove, give a new conditional proof to Lang's conjecture. I wouldn't be surprised by that. You'll definitely get better than what we get, but it would be conditional, and that's how you would do it. I have no interest in doing that, but I invite anyone to do that.
Thank you.
But that's an excellent question. I'll be happy to explain more if anybody wants to hear that, but that somebody should do that. I agree, someone should do that.
Yeah, so yes, Larry.
Yeah, quick question. You know, the analogy between points on an elliptic curve and units in a number field. I was wondering, is there any example like this for number units, number fields?
Yeah, I can't hear it. I can't hear it all.
Oh,
Maybe, can someone
you-
type
you-
that in chat?
you know the analogy between points on an elliptic curve and units in a number field. Is there
Yes.
is there an analog of this for units in number fields?
Oh, yeah.
I mean, because
Yeah, good point. Is this Larry? Is this Larry?
yes, it is.
Hey, Larry, how are you? How are you? Good to see
I'm
you.
actually here.
Actually, even I not focusing on this.
I should come visit you. I'm not so far away. Yeah,
Right.
so, yeah,
Right
Larry,
now.
absolutely. Absolutely, Larry, absolutely, right?
So there is such a result. Because you
Oh, I don't know. I know how to write one down, like you do too, I'm sure. I'm not aware of a result like that, but you could easily do it.
Okay, yeah, it just
Yeah.
seems like you don't have as much structure to play with.
Right. The whole point here in the Diophantine geometry is if you want to study some group and you can write down a pairing of that group with another group you can control and map it into another group that you can definitely control, then you can get these theorems. That's the main point. Yeah.
Any other questions?
Yes, sorry, I've got a
Okay, yeah,
small
so-
question.
Yeah.
You
Please go
say,
ahead.
so first I want to congratulate you because I found absolutely fascinating that using these height pairings, these class group pairings, you can obtain lower bounds. And so I'm really interested in knowing the relation between your pairing and the Maser-Tate pairing.
Yeah. There, I should have mentioned that. When I mentioned Buell, Call, and Solang, I mentioned their pairings, which are very, very close to ours, and they inspired ours. I could also have mentioned Maser-Tate. The only reason I didn't mention that, I guess, for the purposes of this talk, is that pairing. Well, maybe I should have. Yeah. So in many instances, they overlap.
Yeah.
Yeah.
So
in many
they are-
instances, they overlap. Yeah.
Yeah, okay.
Yeah.
Okay,
Yeah. Thank you. That's my oversight.
okay.
Yeah.
Thank you very much.
Yeah.
And